All right, let's get into it. Today, we're going to demystify a really powerful feature in Cisco ACI, Service Graph with Policy-Based Routing, or PBR. Now, if you've ever had to wrestle with complex routing just to steer traffic through a firewall, you know the pain. We're going to break down exactly how PBR uses simple policies to do all that heavy lifting for you.
So, here's what we're going to cover. First, we'll talk about why we even need PBR in the first place. Then we'll get into the essential rules you got to know. After that, we'll look at some common designs, get into some more advanced topologies, and then we'll finish up with the absolutely critical topic of traffic symmetry.
Okay, first up, simplifying service insertion. What's the core problem here? What was PBR actually designed to solve?
Well, in the old days of networking, forcing traffic through something like a firewall could be a total headache. You could think of it like trying to make every car on a highway take a specific weird detour. To do it, we had to build these separate virtual networks, VRFs, and then stitch them together with really complex routing policies. It worked, but it was messy and a total pain to manage. And this is exactly where PBR comes in and just changes the game completely. Instead of getting bogged down in all those routing tables, ACI just uses a simple policy. It's kind of like a traffic cop standing at an intersection. When it sees packets that match a certain application contract, it just points and says, hey you're going to the firewall first. It is so much more elegant and, frankly, way more scalable.
Now, before we get to the fun part with all the diagrams, we absolutely have to go over the ground rules. Look, PBR is incredibly powerful, but you have to follow some very specific requirements to make sure it actually works the way you expect.
Okay, so these are the foundational rules for any PBR setup. First, and this one is huge, the ACI fabric has to be the default gateway for everything. That means for your endpoints and for the service device, like the firewall itself. And why is that so important? Well, because ACI needs to be that central point of control to actually make the redirection decision. The PBR device also has to live in the same VRF as the endpoints it's serving. And just keep in mind, this only works for standard unicast traffic.
Now, for Layer 3 devices, like a typical firewall, things get a little more specific. The device has to be in what's called go-to mode, which is just a fancy way of saying it's acting like a router. You also have to turn off data plane learning on its bridge domain. And, this is critical, you have to manually tell the APIC controller what the IP and MAC addresses of that firewall are. You're basically giving ACI a roadmap directly to the service device.
And things are a bit different again for transparent devices, like an intrusion prevention system. This setup requires some of the newer hardware. You need to have a 2-arm connection to the fabric, and it does have some limitations. For example, your high availability option is only active/standby. So it's a more specialized use case with its own set of rules.
Okay, enough with the rules, right? Let's actually see how all this stuff applies to real-world designs. This is where the concepts really start to click.
We're going to start with the bread and butter scenario, the one you'll probably see the most. We're inserting a single routed mode firewall between two EPGs. Let's say your client tier and your web tier.
Now, take a look at the diagram up top. See, before APIC version 3.1, you had to have separate bridge domains just for the firewall. But check out how in the later versions, shown right below it, the firewall's interfaces can just plug right into the same bridge domains as the endpoints. This was a total game changer, honestly. It just makes the whole design so much cleaner and way easier to manage.
Okay, next up, let's see how we'd go about inserting a transparent service, something like an IPS that just needs to inspect traffic without getting involved in the routing. This is where things get really cool. Check out this diagram. The PBR node in the middle, notice how its bridge domains don't even need an IP subnet configured? This gives you just insane flexibility. Your client and web EPGs could actually be in the very same subnet, and ACI would still be smart enough to redirect the traffic through the inspection device. That's pretty powerful.
So we've seen how PBR works inside a single VRF. But what if you need to go bigger? You can absolutely use PBR to inspect traffic that's crossing between completely different routing domains.
This design is sometimes called a VRF sandwich. You can see we have our client EPG in VRF1 and our web EPG over in VRF2. So what's the secret sauce that makes this work? It's a concept called route leaking. For traffic to get from one VRF to the other, VRF1 has to know about the subnets in VRF2 and vice versa. And ACI handles all of this automatically when you configure the contract. So let's just nail this down. The key principle is this. You put the firewall in either the consumer VRF or the provider VRF. What you can't do is stick it in some third, totally separate VRF.
The magic really happens when you check that little box that says the EPG subnets should be shared between VRFs. That's what tells ACI to leak the routes and make the whole thing work. All right, let's wrap this up with two super important topics. We're going to look at a very common design mistake you want to avoid, and then we'll cover the absolutely crucial concept of traffic symmetry.
First, a quick look at what not to do. This diagram shows a firewall plugged into Layer 2 only bridge domains. This is a big no-no. It will not work. I mean, the name says it all. It's policy-based routing. It needs a Layer 3 gateway to make those redirection decisions. If there's no IP subnet and routing on the bridge domain, the fabric has no idea how to forward the traffic correctly.
So this brings us to a really, really important question. Let's say you've got a couple of firewalls for high availability. When a client sends traffic to a server through firewall A, how do you guarantee that the server's reply comes back through that same firewall A? Because if it comes back through firewall B, that firewall has no idea about the connection, and it's just going to drop the traffic.
And the answer is symmetric PBR. As you can see here, ACI does something clever. It runs a special kind of math, a hash, on the source and destination IPs. You can think of it like a unique fingerprint for every single conversation. Since the client-to-server traffic and the server-to-client traffic use the same IPs, just swapped, they get the exact same fingerprint. And that guarantees both directions of the flow get sent to the very same firewall, which keeps the stateful connection happy and alive.
And this quote really sums it all up, doesn't it? Stateful devices, like firewalls, are all about tracking connections. And to do that, they simply must see both sides of the conversation. So in any design where you have more than one service device, traffic symmetry isn't just a nice-to-have, it's a non-negotiable requirement. Period.
So if you remember one thing from all this, let it be this. Service Graph PBR is an amazing tool. It dramatically simplifies how we integrate services into ACI. But that power comes with responsibility. Your success really hinges on knowing the rules and, most importantly, designing for traffic symmetry from day one. If you get that right, you're going to have a solution that's not only robust, but also incredibly scalable. The only question left is, what are you going to build with it?